this time a power supply, Microset PCS 140. So this is a variable power supply, 4 to 15 and 40 amps, really? However, this one is blown up. They shorted the output and then it blew up. So there's a fuse problem in this. So let's do a teardown and a repair. Let's open this and see what is inside. Maybe we can fix it. This looks really nice. Wow, that is some heavy juice. And this tiny little cap? How many amps of ripple can this do? And that one? Is that it? Really? And okay, it's only rated 10 amps. This output, the rear output for this car plug, but the 40 amps should be available here on the front. I can't wait to see if this will do 40 amps. Okay, so at least they solder in the 40 amps. So this is the transformator. Wow, look at that, nice copper. So this is how they're holding down the FETs and diodes and whatnot. And over here, so this is the input rectifier. Since this one is eating fuses, I bet, okay. So input go to a filter. That is a good idea. To the switch. And that is a little bit of a surprise. This is double disconnected, really nice. And then input goes via the fuse, and I know this fuse just blows up. At least this is what the user told me. And then input goes via double common mode filter, rectifier, and then the capacitors for the DC, and then we have the business end, big nasty transformator, and I see two FETs down here for the primary side, and on the secondary side all I see is one, maybe there's not, one double diode here. So that is the output, and then it goes via this inductor. This is the inductor that will keep the current going, and then it will be DC from here. One tiny capacitor filter and another tiny capacitor. Really? 40 amps? Oh yeah, okay. I think we need to take this apart a little bit more. Let's see if we can find the fault. Maybe we can just measure the diode from here. I think that this is what I will do. Common mode filter here goes to the bridge rectifier, right? So if I put this in diode, let's just look. Ooh, 0.9 volt. And let's try the other way. Also 0.9. That is interesting. So the bridge is working and the short circuit is on the outside of the bridge. That means it's most likely the FETs. Alright, that is my first guess. In 3 seconds figuring this out, let's go and open it a lot more and see if I was right. Before we take this completely to pieces, let's look a little bit more of what we got here, right? So the DC voltage, oh look at that one. There's even another little converter here, right? Maybe it says something what it's doing. So that is also maybe, yeah, I know what that is. This is the switch mode controller for the main power, and the transformator is the gate driver. You can also see the tracks on the PCB. Goes to the FETs down there. Maybe that is not that easy to see. So this is what it's doing. This is the gate driving of the primary circuit. And here we go. That is another little tiny switch mode converter generating the auxiliary supply. Yeah. And what have we got here? So this is the power supply for the display unit. And the voltage adjust, or the amp adjust, going to this switch. And this is how you select voltage or amp display. So this is all it's doing. Analog interface to the display. And here is the voltage output adjust for this one. Really nice. Oh, there's an op amp. Oh, this is for amp. This is for amp protection, I guess, yeah? Interesting. So it's measuring amps over this one. This is most likely the current measurement. Here we go again. This is the bridge. The two capacitors. They are in series. Two resistors for discharge and for, of course, voltage dividing. This is the transformator return via capacitor. This is a very normal way to do this. The two power MOSFETs are here. The two snooper circuits. And the transformator is just one winding from all these four and to these three. So this is the transformator winding back to the center point. So this is a half bridge push-pull, and this will be the trigger transformator. One winding here goes to one FET. This is the gate and the source, and the gate and the source of the other one goes to this winding. But see, there is a really funny, super bad design. Let's see if I can make this more visible. Look what they have done. How the hell do I show this? Yeah, okay, like this. See, this is the capacitor from the primary to the secondary side. This is very, very important for closing the loop in the power supply. All right, look at this. They're sharing the track with the gate drive and with the main power drive for that FET as well. What kind of beginners are they? Look at that. All they had to do is take this and put it this way in a separate track that is not sharing peak currents, peak shit. Oh, this is really, really not how you want to do this. Don't share your tracks, my God. All right, there is 0 ohms between in the rectifier, plus and minus, but since this output goes directly to the two FETs, you don't really know by now where is the short in both of the rectifier diodes or both of the FETs. So it can be both, but it's a little bit difficult to take out the FETs. So I think I will just take out the bridge first, because it's the most easy thing to do. Then we'll know for sure what it is. Oh, damn it. The bridge was all right. So now we need to dig all the way in here. So those two screws we need to take out, and these two, and then we can, let's see how do we do this the most easy peasy way, man. Yeah, we got a winner. And see, they are completely shorted out all the way around. So here we go. It turns out that these two babies, they're IGBTs, and they're both completely shorted. Fantastic. So what I've done is I shorted off both of the sources, or the emitters, sorry about that, of the two transistors. And that means I can connect two probes on the two gate driver signals, just to test that everything else seems to be working. And then I just connect a little bit of mains. Of course, everything is on double isolated transformators and the variable transformators, and the scope is on isolated transformators. I'm very, very careful about what I'm doing here, so please don't copy this unless you know exactly what you're doing when you're playing with switch mode power supplies like this. You need to be careful, all right? So carefully crank up the input and monitor the current. Of course, you shouldn't expect any current at all in this case, just to get the auxiliary supply up and running. And when that is up and running, you'll get gate drive signals. Yay! So what I've done is I've just set the pot meter for 6.3 volts. And so what I'm doing is I'm inputting 6.3 volts from an external supply into the input, like feed it backwards in, and then I'm checking out the two gate signals and see if I'm turning up, and this is up, and now I'm turning the voltage down, then I get more PWM. So this is the maximum duty cycle, and the minimum duty cycle is 0. Fantastic. So that means voltage regulation is working. Now I will test the current regulation, or current protection is working. And when all this is confirmed, then we can put in new IGBTs, and then this one will be repaired. So how do we test the current? There is a current sense resistor. Okay, I will maybe turn this off so we can poke around with it. So the current sense, it's this big baby. I will disconnect this one and put in a 1 ohm resistor or something low ohm, of course, but enough so that I can input some current, so I can make a voltage difference. So when I can raise a voltage over this, then the system here should figure this out and then turn down the PWM. So this is what I need to see. So this is where the sense resistor was mounted. Of course, it is measuring the voltage in this point. That means including the soldering to the resistor. And then current flows from this point and out. And then it's measuring the voltage in this point. So that is including, you know, the voltage drop in the soldering again, right? So let's measure the sense resistor with a 4-point Kelvin. That means it is, depending on how I move this, but around 1 milliohm. So to test this for a 40 amp current limiting or limit or protection or whatever, I would expect 40 millivolts, but also the connection here, I think I should expect a lot higher actually. So now I will try and put in a resistor here, and simulate the voltage input here and see what happens. This is the sense resistor. Now 100 milliohms instead of 1 milliohm. So that means I only need to give it a lot less current, right? So I feed in some voltage just to check regulation. So this is the PWM, and this is the voltage at the moment. I'm only playing with the voltage. So first we turn the voltage up and down here, and then I verify that we are in regulation. So this is fine, about in the middle of regulation. Then I go over to current, and now crank up the current a little bit of milliamps. Let's go into finer milliamps and then crank up the milliamps like this. And then I monitor the PWM. Oh, I'm a muppet. I should of course turn on the output. Duh. So let's try again. Crank up the milliamps like this while looking at the PWM. And then what happens is PWM goes low. So the beep beep here is actually the power supply complaining. It guesses that the output here is short circuit. Of course it is, because it's a very low resistor that I'm putting in a little bit of voltage over. But you see, current regulation or current protection actually works, and it can go in constant current mode. So this is what we have right now. It is in current regulation, so that works as well. Fantastic. That means let's put in some new IGBTs and we should be done. All right, let's try something funny. See, this tiny little, why can't we have any light in here? Here we go. So this tiny little TO220, this is Infineon CoolMOS. This is a very, very special high voltage, high current MOSFET. So instead of using IGBTs, look how big that is. Ooh, let's try with FETs instead of IGBTs and see what happens, all right? I would expect the efficiency to be a lot better. Of course, they are also a lot more expensive. But so that is, of course, why they're not using stuff like that. But let's have a look and see what happens. Bad luck happened. That is exactly what happened. Or was it bad design that happened? Have a look at this. So the two wires for the voltage feedback or the voltage adjustment, that is in fact the voltage feedback coming from the output voltage that goes via those wires. So that means when you crank up the voltage, you increase the resistance from the output. So the regulator will think that we have a little bit less output, and then it will crank up the output. But what happens if you have dust or bad connections in the wiper? That means you lose the connection between these two wires. That means the regulation system will get zero. It will think that there's zero, but there is actually something, and then it will just crank up the PWM and it will blow up the entire thing. So this was just badly and wrongly designed, because I had, of course, perfect output, perfect regulation. I could load the damn thing and everything was super duper good until I played a little bit with the voltage knob, and then it was just kaboom, and my new and fantastic FETs, they're just blown up just like the previous IGBTs. So this is exactly what is causing the problem in this power supply. All right, so now the regulator is of course also blown. Well, this time it is the Zener diodes. We got some protection, some Zener protection on each of the gate signals, and those are now shorted. So that means this is just one big short circuit on the output of the two gate signals. So all those resistors here, they're just red hot, and it's using a lot of power. So I saw this immediately. I could even smell it. So this needs to be repaired before I can play anymore with this. Okay, that was easy. This is the schematic of one of the gate driver signals we got here. And what you see, we actually got a full bridge driver. There's only one coil on the primary side, so that is definitely a full bridge. So that is really nice. And the two halves, they're made exactly like this. And in my case, the only problem was the two center diodes. They're shorted. There's absolutely nothing written on this component, and it's completely shorted. So my best guess is this will be 15 volts Zener. So that is what I'm going to put in. The turn off PNP works in both cases, so I just plop it back in. It shouldn't be anything special, just a turn off low voltage PNP transistor. So yeah, this is how it works. Another little thing to mention, look at this very, very big PCB. It is of course a single layer PCB, and it will be different from all the different models they design. The driver PCB is a 2-layer PCB. It also looks like it is a lot better quality, and this will of course cost a lot more money because it's double-sided compared to a single-sided PCB. But look, all this space here and parts aren't really that closely spaced. You could easily fit the components on this piece of PCB and just have one PCB instead of two. But of course then the big PCB would have to be a double-sided PCB to make this design good and optimal. So to cut cost, of course they make a little expensive per square area in 2 layers, and then they just reuse this design for all the different power supplies, because all this do is drive FETs and measure output voltage and current and stuff. This is a total versatile, reusable design. So here is a little bit of what I found, just in case any of you ever needed to repair one of these. Let's start by looking at this module. So this module is mounted like this. So this is the pinout, gate and gate, and then the minus. So then you have the current measurement, the overload LED, a positive 14 volts supply, feedback voltage from the voltage pot meter, an unused signal that I don't know what is, NTC resistor, and the fan control. So see here, the NTC resistor is just mounted to ground. Then the positive signal from the fan control goes via a resistor to an NPN. And there is a minimum speed of the fan to ground. And then of course the transistor just short this signal to ground when it's too hot. So it's that simple. So then we have the 14 volts capacitor, the diode from the transformator. This is the secondary side of the flyback. So that diode makes the 14 volts. See, there's another diode and a resistor and another resistor. So this is driving the optocoupler, and this is creating the regulated 14 volts, that Zener and resistor. So in case you don't have the 14 volts, this is where you have to look. The op amp down here is doing two things. The bottom half of it is actually measuring or amplifying the voltage difference over this 1 milliohm current sense resistor. So see, this point here goes straight into the supply and to the positive pin, the positive input of the first op amp. So the negative input, there's a resistor to the output and a resistor to the other side of the sense resistor, right? So this is 1K and 18K. So that will be 19 times the gain, right? And then there is the resistor, the little trimmer for the current display. So it will read out the correct value. This is the current limits. And this is just a series resistor from this. So this is a very, very low voltage signal that goes all the way to the current sense input. But note this thing. There's a diode here from the other output of the other op amp that is connected to the current sense signal. That is because the other op amp here, there is a Zener, about 5 volts. You have 5 volts on the, so this is a reference or a voltage you compare with. And then the output voltage. See, this is where we measure the output voltage. The output voltage is actually going this way. So this is for the display, and this is the potentiometer on the front in series with this, right? And it goes to the voltage control. So that means if the output voltage is more than 21 volts, this op amp's output will pull the current signal high. So this will shut off the PWM. All right. So this is how it works. All right, here we go. I have now disconnected the voltage set potmeter, and I'm measuring the output PWM while I'm turning the input voltage. I'm feeding in input voltage back because I'm not running with any IGBTs or any FETs. So that means I can still see how it's working, right? So if I crank up or down, I get more and I get less PWM. So 20.6 almost is the output voltage if there is a loose connection in the potmeter, and the over voltage protection was set for 21. So this is not so good. But see, there's another trimmer out here, the V out. What happens if we play with that one? So look at that, huh? The original IGBTs and the field effect transistors I was using, they actually outperforms for these on all specs, by the way. But now, though, that is some bad boys. Let's try with that instead and see what happens. So we are back, we are happy, the damn thing is running. Got a little bit of ripple and noise and whatnot. And I'm only loading it with 5 amps. Of course, let's have a look. Yeah, okay, it is in 20 megahertz. Let's see what happens. Okay, 50 millivolts division. But most likely you would like to look at the 20 megahertz bandwidth. So that is 10 millivolts per division. So it's actually not that bad. Really? All right, see ya.